Good afternoon, everyone. Our talk today is Deep Puzzling, Binary Code Intention Hiding based on AI Uninterpretability, which is completed by me and my colleague, Jifeng. We named it Deep Puzzling because it uses AI technology to show a variety of behaviors, which makes people feel puzzled. We are all from the Zhuque lab of the Tencent Security Platform Department. The Security Platform Department has been with Tencent for 16 years and dedicated to the protection of QQ, WeChat, Tencent games, and many other products. And Zhuque Lab was founded in 2019, focusing on red teaming and AI security. Some researches have been published on Hack in the Box Conference, X-Focus Conference, Proof of Concept Conference, etc. Please allow me to briefly introduce ourselves here. Jifeng has more than 10 years of experience in information security. His research mainly focuses on vulnerability, advanced threat analysis, reverse engineering, and AI security. And I am quite familiar with deep learning and data mining methods. Now, I mainly work on AI-enabled security research. Our speech today is mainly focused on the following 5 parts. In the first part, I will give you a basic overview about the intent hiding. Then, I will explain some background and its importance to security, especially why we use AI here. After that, I will introduce the deep puzzling framework in detail, such as feature extraction, binary code generation and repair. And later, the demonstration will be illustrated, as well as the reverse analysis. Finally, I will summarize this talk. Okay, let's dive into the intent hiding. First of all, let's learn the evolution history of malware. With the fierce offensive and defensive confrontation, we have witnessed various novel malware attacks. The key word of the first generation is obfuscation. Its main feature is continuous mutation in the code. And the second generation is encryption. Its main purpose is to evade static detection by hiding the payload. The third generation is evasive malware. It tries to avoid being analyzed with sandbox anti-detection. And the fourth generation is the targeted attack. It tries to disclose only at a target. It can be seen from these trends that attacks are becoming more refined and more purposeful. there are more and more judgments and constraints on the environment. This phenomenon cannot help but cause us to think about intent hiding. Okay, let's see the important role of target positioning in modern cybersecurity. Intent hiding. Simply put, it means meeting the right person and doing the right things. The most important goal is to hide one's key behaviors, avoid being discovered by the public, and exert the greatest power at the most appropriate time. Target positioning is the core of intent hiding. It can narrow the scope of influence, avoid large-scale detection, and increase the concealment of actions, so it is often used in APT attacks. The Stuxnet attack is a very famous one. Just like the right finger illustrated, in order to achieve target positioning, we need to collect running time data, such as physical hardware, network connections, documents, pictures, etc., and later to make further decisions based on these findings. In fact, security researchers from IBM have proposed an intent concealment framework for target positioning as early as 2018, which called DeBlocker. It uses AI algorithms to identify the target. As the finger shows, only the key generated by a specific person can decrypt the payload and release the attack. It will not show any malicious behavior under other conditions. This approach is quite shocking, allowing people to see the power of AI attack. This is key guaranteed security. In their approach, a face image is used as input. A detection algorithm is used to generate high-dimensional features. And a generation model is also used to build a robust key. Then this key can unlock the payload and start the attack. Therefore, the length of the key is critically important, and it is directly related to the difficulty of cracking. However, this does not mean that the framework has no weakness, especially for reverse analysts. Debugging will reveal everything. The cracker analyzes the program and will soon find that the core of the entire framework lies in the key, and the attribute features collected by the program will reveal this clue. Because the face attributes are collected, the intention must be related to a specific person, based on our normal reasoning. Therefore, There are some possible methods for cracking this framework. The first method is to enumerate the keys inside the program directly. The second is to brute force the input attributes. And the third is to input some deceptive attributes. Considering the shortcomings analyzed here, new ideas popped up in our minds. From attack to defend, maybe it brings us different ideas. Just like the two sides of a coin, these advantages and disadvantages inspire us that we may be able to design a balanced plan. Combining intent hiding and anti-debugging, we will get better binary code protection. For the attacker, it can hide the attacker intent. For the defender, it can protect the core code from being reversed. We have studied some possible improvements. The motivations can be these. The first is to perform multitasking, so that some of the tasks can be anti-debugged, while the main work can continue. The second is to use implicit features. Hide the intent in a large amount of plain data. This will greatly increase the enumerated space for guessing. The third point is generated payload. Disguised as an ordinary AI application, the program does not store the payload directly. The last is to use an end-to-end model to avoid tampering and traversal of the intermediate value from the AI model. After discussing these ideas, we hope to design a powerful binary-level code intention hiding framework to exert great power in actual combat. Now, let's analyze the significance of this design for security. Let's first look at the boom of artificial intelligence. With the rapid development of modern deep learning methods, AI has been widely used in many fields, such as agriculture, industry, finance, medicine, and entertainment, along with many other revolutionary applications. It has profoundly changed our lifestyle. It is no exception in network security. We have witnessed too many successful cases. For the attacker, we can use artificial intelligence to find vulnerabilities, Trojan avoid killing, spear phishing, and even automated penetration testing. And for the defender, we can perform intrusion detection, web application firewall, malware detection, and user behavior analysis. The efficiency of artificial intelligence can complete these tasks quickly and realize intelligent decisions to a certain extent. The elements of the success of these applications can be summarized in the following two aspects: massive data and the patterns behind them. AI is very good at imitating, and the massive parameters allow them to approximate any high-order complex function and adapt to the conditional probabilities in different contexts. At the same time, the contrast of positive and negative examples allows the AI model to learn a better decision boundary, as shown in the figure below. The sample generated by the generator and the original sample can be effectively distinguished by the discriminator, which can guide the generation of more effective adversarial example. Here, let's review some characteristics of AI. In modern deep learning, sequence generation plays an important role. The core is the encoder-decoder framework. Now, let's learn the generative characteristic of AI. The encoder-decoder architecture can handle inputs and outputs that are both variable length sequences. Thus, is suitable for sequence transduction problems, such as machine translation. The encoder can take a variable length sequence and the input and transforms it into a fixed shape hidden state. In other words, information of the input source sequence is encoded in the hidden state of the encoder. To generate the output sequence token by token, a separate decoder is used to predict the next token based on what tokens have been seen or generated, together with the encoded information of the input sequence. Since many parameters in the original model are redundant, generating ability naturally means memory. And autoencoder is one of the successful applications. An autoencoder is a type of artificial neural network used to learn efficient coding of unlabeled data in an unsupervised learning way. The encoding is validated and refined by attempting to regenerate the input from the encoding. So it has the following features. First, no labels are needed. Second, it means smaller model size. These make them popular in real products. While the AI model is powerful, it also has some special properties. Here, we study its black box characteristic. Traditional statistical model based on logistic regression and decision trees usually have good interpretability. We can see the feature importance. However, AI based on deep learning method is very different from them. First, the AI model usually consists of a network structure and weight parameters. Just like the right fingers as shown. The network structure defines the flow of the vector, and the weight parameter determines the transformation of the input. Second, it is usually difficult to explain whether a network structure can work well, and in most cases, it is designed based on experience. Third, for the weight parameter, we cannot explain its meaning. Only know that after the transformation of these parameters, we can get expected output. Fourth, it is usually difficult to explain which features of the original data that the AI model has learned. We only know that it will calculate a reasonable output on similar datasets. In general, these characteristics make artificial intelligence a black box to a large extent due to the lack of theory guarantee. Knowing it, but not knowing why. What do these characteristics mean? We summarize it as follows. First, powerful sequence generation ability means greater memory capacity. It's easy to remember a passage, and it is able to adjust the decoding output according to the input of the encoder. Second, advanced memory ability means fault tolerance. It is able to restore damaged data. And last, the uninterpretability characteristic of AI means its natural difficulty in reverse analysis. It is almost impossible to modify model parameters in a brute force way. The causal relationship between model input and output is not clear. Even if the AI model is obtained, it is quite difficult to know which data and features are really at work. Considering the cognitions above, we are the first to propose AI-enabled security practices based on the generative ability and uninterpretability of the AI. Combining the characteristics of AI and security can give us a higher level perspective on the current security situation. We hope to make full use of AI's discrimination power, generation ability, fault tolerance, and uninterpretability characteristic, so as to explore the possibility of artificial intelligence-powered attack and defense. Okay, let's continue. It's time to introduce the design details of the deep puzzling framework. The key idea of this framework is to avoid explicit conditional judgments during code execution, such as if conditional judgments, regular expression matching, while conditional judgments, and hash value matching. All decisions are made by the artificial intelligence in order to take advantage of the uninterpretability of AI to make difficulties for the reverse. Let's keep in mind that we simulate everything with AI. Specifically, the overall data flow of our framework has the following steps. Step 1. Obtain a large amount of plain data. Our intentions can be hidden in this data in some kind of backdoor. Step 2. Pre-processing. Encoding this raw data into labels. Because the AI model cannot deal with charts directly. Third step. Use feature extraction and generation models to process the data above, then output probabilities. Fourth, decoding the probability to get preliminary output. For instance, a list of indexes in the pictures named middle output. Fifth, fix some error with an error correction model. Sixth step. And then we will get the final output. It contains our design intentions. Seventh, encode this data into binary code and execute it. The whole process is described in the way of data flow previously. From the perspective of running time, it can also be viewed as 3 parts. The first part is input data and feature. The next part is AI model. And the last one is execution code. The first 2 stages are completed offline. Only the last one is exposed. Okay, now let me introduce the details about the design. First, let's reveal the details of feature extraction. In the AI algorithm, feature extraction directly determines the final effect of the model. Statistics-based methods often need to manual features so that the intention may be guessed by the reverse engineer, while deep learning-based methods only need to encode the original data. We use this black box manner here. In our scenario, there are 2 main problems that need to be solved. One is how to extract high-dimension features from massive raw data effectively. Here, we use a network architecture similar to text CNN, which is a network that uses convolutional block to extract features. After encoding the original data, one-dimensional convolution block is used, and then concatenate the output of these basic blocks together by dense connection. And then the feature vector is formed. The network connection is shown as the middle finger. This network structure has been proven to help to improve the quality of feature extraction for better gradient propagation. The other problem is how to ensure the robustness of the feature output under different input data. Considering the scarcity of data resources, our main solution is to supplement the training data through data augment methods, such as crop, reorder, and changing upper and lower case to maintain the model's stability. Here is a detailed illustration of the calculation process of convolution and pooling method in feature extraction. Let's see the convolutions. The input is a two-dimensional tensor with a height of 3 and a width of 3. The height and width of the kernel are both 2. The shaded portions are the first output element, as well as the input and kernel tensor elements used for the output computation. And we will get the final result, 19. As for pooling, it is very similar to convolutions. We can think of the pooling window as starting from the upper left of the input tensor and sliding across the input tensor from left to right and top to bottom. At each location that the pooling window hits, it computes the maximum or average value of the input subtensor in the window, depending on whether max or average pooling is employed. After the features generated above, we passed it to the decoding part to generate the payload. The whole steps are as follows. Step 1. Add a dimension to the n-dimensional features and expand it to m plus n dimensions repeatedly, where the m is the max length of the decoded output. Step 2. Use a bi-LSTM network to further process the features to generate hidden features. LSTM network is a basic component of deep learning with good performance, which processes the input text in order, while bi-LSTM is bi-directional LSTM, which can process from front to back and from back to front at the same time, and usually has better performance. Step 3. Use a fully connected layer to cross the hidden layer features. This will give us the desired output dimension. Fourth step. Use a softmax function to output the probability of each position character. and take the one with the largest probability as the decoding result. The generative model and the feature extraction model are cascaded together, which means that they are optimized at the same time during the training phase, and the payload is generated end-to-end. In theory, the payload has been generated after the first two steps. But since the AI model is a probabilistic model, which means all decisions are not precise, even if the accuracy of the model is beyond 99%, there are still a few decoding errors. For computers, the slightest loss is 1,000 miles away. It is inaccessible. Therefore, it is vital to fix the small number of errors. Here, we use an autoencoder to achieve this goal. The rule of this model is to try to restore the original input. The input is part of the shellcode that may be wrong, and the output is the correct shellcode. And the stability of the data augment method is used at the same time, so as to reduce the probability of failure. The construction of the entire model is relatively simple, as shown in the figure on the right. The classification loss function is used to optimize the model, and the model is forced to correct the errors. In the figure, we can see that the wrong number 0 is corrected to 10. Based on the principles above, I will introduce some of the experiments and the corresponding analysis we have conducted. Let's first look at the target setting. There are 3 targets in the experiment, namely ordinary people, developers, and reverse analysts. For these 3 groups of people, different intentions are made. For ordinary people, the environment is characterized by a clean office system, which executes a message box code. For developers, the environment is characterized by the installation of development tools such as Visual Studio, Python, SSH, and a calculator code is executed. For reverse analysts, the environment is characterized by debugging tools such as IDA, FRIDA, and WinDebug, and no code is executed. There are 3 main steps in implementation. Step 1. Make dataset. We collect environmental data when the program was running, and then randomly sort it, crop it, etc. to form a string of about 20,000 charts in length. The label is the type of target intent, and the corresponding shellcode. We have also made shellcode error correction data, which allows from 0 to 2 errors per 10 bytes. It should be noticed that if the error rate of the input is very high, the output is also the same, so as to avoid recovering shellcode by many training. Step 2. Train and convert models. Split a part of the data as validation sets and use TensorFlow to train the model to ensure that the accuracy is above 99%. When the model is trained, the default storage format is HDF5. We use tools to convert it into a JSON file and write it as a resource file into C++ project. Third step, C++ reasoning. The execution flow is collect data, load model, decode shellcode, fix code, and finally execute. Here is a detailed description of the input and output data. The input data is the standard information when the program is running, such as process name, file path, start menu, registry key, etc., most of which have nothing to do with the intention. After processing by the AI model, the output is between 0 and 255 unsigned char that can be easily converted into shellcode. It should be noticed that the input and output here must be filled into a fixed length, such as 18,300, and irrelevant characters will be discarded during decoding, so as to keep within bounds. The main part of the AI model is a code generation model. The details of the constructions are shown here. From top to bottom, it mainly includes data, features, generator, and output. We'll introduce them one by one. After the data is input, embedding is performed first, so that the discrete values become continuous vectors. Then these vectors are processed by different Keyun respectively, followed by max pooling layer, and then new Keyun, etc. And finally, these pooling vectors are concatenated together to form the final feature. Finally, these features are processed using the BioSTM model to generate a preliminary binary code, which is illustrated before. Here comes the demonstration. The following figures show the execution result of this demonstration system. For ordinary targets with no special software, the system executes a message box code. And for developers with some developing tools, The system recognizes and decodes the shellcode of the calculator. The third pictures show that for debuggers, the system does not execute any code, which has an anti-debugging effect. Beyond the demonstration, we also performed a reverse analysis of the code from the perspective of the cracker, and we can get the following findings. First, we do not seek to use any techniques to obfuscate the source code, as shown in the figure on the right. The execution logic of the code has not been modified deliberately. Second, it's not difficult to locate the code that runs the intent. The difficulty lies in when it will be triggered. The key point is that the address of the decrypted code is obtained in a dynamic way. Third, if the ECX value here is not the input of our intended purpose, it will be the run value, and there will be no payload running. We can see the important role of multitasking here. As shown on the right, the input we mentioned here is a high-dimensional space vector. It is difficult to infer the real purpose simply by modifying some of the data due to the robustness of AI model. It is fault tolerance. Here is the conclusions for analysis. First, if the trigger environment is not met, the ECX value cannot be obtained. Second, finding rows in massive data is extremely difficult. Third, the AI model is neutral and does not contain any intent code directly. This is very different from previous designs, as shown in the code below. The execution process is clear, but the details are not. It's hard to go inside. The talk illustrated here is over. Let's summarize this speech. We propose a binary code intention hiding framework based on deep sequence generation network. We conduct an experiment to hide message box and calculator to avoid being discovered in the debugging environment. Our experiment confirmed that due to the powerful distinguishability and uninterpretability of the AI, it greatly increases the difficulty of analysis for reverse engineers. The combination of AI and security will magnify the offensive and defensive situation in cybersecurity. Here are some materials that may help you understand the technical principles and details, such as FDeep, CNN network, encoder-decoder model, and autoencoders. If you are interested, you can continue to read them. My talk is over now. Thank you very much for watching. If you have any questions, you can contact me and Jifeng with email, or continue on the Discord channel. Thanks.